This video, we're still working through our absolute and relative change practice, and we're going to be focused on questions 3 and 4. Both of these questions are sort of building contingency tables and then finding probability, but these contingency tables are a little special because they deal with testing results and focus on this idea of tests that come back with false positives or false negatives, which are not things we really want. And so a good thing to keep in mind, so here we have a table on number 3, and it's looking at Cologuard's at-home colon cancer test. And we're told that it's said to be more than 90% accurate. In fact, it's 91.7% accurate. And so what that means is 91.7% of the time, if you have colon cancer, this test is going to find it. And so this box right here, 97.1% of the time, we're going to get that correct result. If you have cancer, it's going to tell you. And then 91% of the time, if you don't have cancer, it's also going to give you those results. So I've sort of highlighted in green the boxes that it's going to get correct. But at the same time, yes, it gets it correct 91.7% of the time. It does mean that 8.3% of the time it gets it wrong. And so there is a chance that you don't have cancer, but the test is going to find the cancer. And so these are what we call sort of false positive results. So the test told me that I'm sick, but I'm not actually sick. And the same thing with what we get is what is known as a false negative. The test says I'm not sick, but I actually am. And so these boxes I highlighted in red because they're bad. They're when the test gets it wrong. And so we want to be able to sort of, based on a group of people, how many could we expect in each of these regions? And then off of that, let's find some probabilities. So this first step is to sort of know, in general, how many people actually have colon cancer. And the National Cancer Society tells us that about 5% of the people will be diagnosed with colon cancer over their lifetime. And if we're looking at a group of 5,000, we then want 5% of that number. Now, 5% of that number are going to have colon cancer. And so what that 5% actually, it's going to be down here. It's going to be this box right here. So 5% of that 5,000, so that would be 0.05 of 5,000, would have that they would have cancer. So we're going to go over to our calculator, 5,000 times 0.05. And so that's, and I'm going to just make it in a different color. My work's in purple and the final values are in blue. So 250 people have colon cancer. Now, you either have colon cancer or you don't have colon cancer. So everyone else then would not have colon cancer. So we're going to do 5,000 minus 250. So that comes out 4,750 don't have colon cancer. And just so you know where I got that number from, I like to show my little steps out here. All right, so we have sort of our totals in each column. Now we're going to use these totals to then fill in the boxes above. And so we're going to go back to that 91.7% number we have up here. Because remember we said the test gets it right 91.7% of the time. So that means of these 250 people, it's going to correctly diagnose that percentage of them. So basically, I need 91.7% of my total below. And so I'm going to do 0.917, so that's 91.7% as a decimal, times that 250. So of those 250 people. Now, you'll notice I get a decimal. I'm just going to round this decimal down. So that's 229 people who got correctly diagnosed with colon cancer. Similarly, the test is also going to correctly get people who don't have cancer 91.7% of the time. Excuse me. So 91.7% of 4,750, because those were all the people who didn't have cancer. Now you'll notice this time I have a decimal, but with that 0.75, that 75 hundredths, we are going to just round that up. So that's going to be 4,356. Those are all the people the test got right. Well, the test is also going to get it wrong, and so we are going to do a little bit of subtraction to fill in our wrong boxes. And so let's start with the people who have cancer, but the test didn't find cancer, so they got a false negative. So there were originally 250 people with cancer, 229 got a correct test result, with left 21 who got incorrect test results. Similarly, there were 4,750 people who didn't have cancer and 4,356 who got the correct test result, which left 394 people who are panicking right now thinking they have cancer when they really don't. Now, whenever I'm doing these charts, I do like to double check that all my numbers work. So what I'm going to do now is I'm going to total my rows just to make sure that all the numbers add up. So I'm going to do, 229 plus 394 in this top row, and I'm going to do 21 plus 4,356. So going over here, I have 229 plus 394, and I get 623. And then I'm going to repeat that process, 21 plus 4,356. And don't be like, oh my goodness, I could do this adding in my head. Yeah, just put it in a calculator. Make sure you're adding them right. Because I want to now double check that those subtotals add up to my actual total. Especially when I've rounded, I just want to make sure that all my numbers add up correctly. It's the beautiful part of a contingency table is that I can do this double checking. I can sort of double check that my math work throughout worked. And notice my two subtotals do add up. I'm checking that they add up. They added up to 5,000, so good. Woohoo! Everything worked out. All right, so now we have the table. Now we're going to go do some probabilities. And this is some ways that sometimes the more challenging part because we have to interpret what the question is asking and make sure we're reading it correctly. And that's, in my mind, that's always the hardest part with probability questions. Okay, so what is the likelihood? Likelihood's just another way to ask what is the probability, what are the chances, what are the, those sorts of things. So what is the likelihood that a person in this group tested positive for cancer? So notice it's just in this group. So that means we're looking at everyone and we're looking that they tested positive. And the key word here is tested, not that they had it. So we're looking for the probability that someone got a positive test out of my 5,000 total people. And the test finds cancer, remember, would be a positive test. This would be positive. Test finds no cancer would be negative. So there were 623 people who tested positive, and that would be about 12.5%. At this point, I'm not going to show putting the fractions in the calculator and getting out percentages. I think we've done that enough times that we should feel pretty confident. I want to focus more on where am I getting the values from. All right, the next one. What is the probability of receiving a false result? So probability, and I'm going to put in here false result. Now, we've already highlighted these in red because we said there were two ways you could get false results. One would be that false negative where the test tells me I don't have cancer, but I actually do. And that would be those 21 people down here. And then the second one is the false positives, the people that the test finds that they have cancer, but they actually don't. And so that would be the 394 people. And I do like to sort of show it, add it out. If you're like, I'd rather just make one fraction, that does add up to 415 out of 5,000. We're still out of the total. We have no subgroups here. We're just looking at everyone. And so there's an 8.3% chance of getting a false result. And that works with the number we have out here. Look, 100% minus 91.7 is 8.3%. So it's right 91.7% of the time, and it's wrong 8.3% of the time. So that makes sense. That is, woohoo, we filled in our table correct. Another check. All right, and last but not least, oh, ding, 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 I see a keyword. The keyword is given. We see that word, and in our mind, we should be going, we have a subgroup. So given that a person's test finds cancer. So there is our subgroup. So our subgroup is that they have a positive test. What is the likelihood that the results are false? So when we have a subgroup, we're not looking at everyone in the whole entire table. We are only focused on people who have positive test results. So this row I've highlighted in yellow. And of those, there are 623 people. And in that row, 394 of them got false results. They were told they had cancer, but they actually didn't. So we would say there are 394 out of those 623. And when you go and find that percent, you sort of go, whoa, because that means 63.2% of the people are getting incorrect results. So yes, that 91.7% seems great, but when you just sort of focus in on that subgroup, it gets a little more worrisome. And you go, ooh, maybe we could make this test a little better. Uh, and when they're approving medical tests like this, they do look at data like this because it helps them see, like, is this a good test? Are we happy with it, et cetera, et cetera. All right, let's try the next problem. It's very similar to this first one. But again, let's focus on those like probability. I'm going to do a little less highlighting in the table this time around because hopefully this first one sort of helped solidify what you need to do. Now, I do want to talk a little bit about rounding on this table because what you're going to find is the numbers, there's sort of, depending on how you round, you're going to get different answers, and that's okay. Either one works. You just need to make sure in the end all your numbers in your table agree. All right, so we can assume that 1% of breast tumors are malignant. So malignant means you have cancer. And a mammogram is a type of screening process that's used to sort of see if a woman has malignant tumors in her breast. The screening is only 85% accurate, and we want to complete the following table below. All right, so we have 5,000 total women, and 1% of them have malignant tumors. So we're just going to start there. So we have 5,000 times 0.01, and we get a nice even 50. And so if 50 women have tumors, then everyone else does not. So, 5,000 minus 50. So that's 4,950 don't. All right, the tests are 85% accurate. So of those 50 women, 85% of them are going to come back with a positive test. So if I put 50 times 0.85, you'll notice, I have 42.5. So yes, technically at 0.5 we round up, but we could also round down. And this is where you need to sort of make a decision. And here's the other thing. If I go do my next number, so 4,950 times 0.85, this is also a 0.5. So on the last problem, we had a 0.25 and a 0.75, so we rounded down in one place and we rounded up in the other. And that's basically the rule of thumb with these tables. So if I round up for positive mammograms, then I need to round down for negative ones to sort of balance it out. Because overall, the values I get, the 40, so like the 42 plus 4208, that needs to be 85% of 5,000. And in order for it to be 85% of 5,000, I need to round down in one place and up in the other. So it's really your pick, whichever way you want to go. On the answer key posted on Canvas, you will see that I did out all of these problems using both sets of numbers, one's in light blue, one's in purple. And you can sort of decide, check based off which one you chose to do. In this case, I'm going to use 42 for the positive cancer tests and 4,208 for the negative cancer tests. Again, you could also use 43 and then 4,207. Obviously, it will change your answers within your table slightly, Both are correct. And it does alter a few of the probabilities a little bit, but again, we're aware of this, and we're talking minor, minor, off a little bit. All right, so if 42 got positive tests, then of those 58 would have gotten negative tests. And if 4,208 came back with negative mammograms here, then 742 got positive ones. And then, we total each of our rows, 784, 4,216. And this one, especially because of the rounding, always do a double check of, do my two rows add up to the right total? And if you had rounded both of those values down, you might find that your rows aren't adding up correctly, but they do in this case. So woohoo, we're good. So key was rounded up in one box, rounded down in another box, and then it all sort of works out pretty handy dandy. All right, let's focus on the probability part because I'm betting that's the more challenging side of things. I know the rounding on this table was a little weird, but besides that, it was sort of, similar to the last one. Okay, so we have, what is the probability of getting a positive test result from a mammogram? This is just like the first one over there. So we want probability of a positive, and I'm just going to say mammogram, M for mammogram. So we're looking out of the group of 5,000, and positive mammograms would be everyone in that top row. And so that's 784 out of my 5,000. And if I put that in a calculator, I would get 15.7%. So next one, suppose a patient has a positive mammogram. What is the probability that she really has cancer? Ooh, so this is a good one where maybe it's not exactly our keywords, but it's still a conditional probability. So suppose a patient has this. I know this is true. So I know this person got a positive mammogram test result. I want to know, what are the chances that the person actually has cancer? So cancer given a positive mammogram. And so the 784 is all the people I care about. And of those 784, 42 of them had cancer. And 42 out of 784 is only 5.4%. So of the people who got positive test results, only 5.4% of them actually had cancer. When you look at it that way, you go, whoa, that's not that many. You start to go, Okay, the next one. What are the chances of a positive mammogram given, keyword, given that a patient has cancer? So we're basically flipping the probability we had up on part C. So this time my subgroup is that we know they have cancer. And what are the chances of them getting that positive test result that let them know? So this time, our subgroup is the 50 in that first column. And, 42 of them were told that they had cancer. And basically this should be that 85% correct rate. Now, you'll notice that the percent only comes out to 84. And the reason is because we rounded. Had we rounded up, it would have come out to 86. Had we kept it at the 42.5, it would have come out to 85. So, this is where the rounding sort of took a little bit of an effect. But, okay, my thing's right. All right. Oh, suppose a patient has a negative mammogram. So we have another conditional one here. So my subgroup here is my negative mammograms. So negative mammogram. What are the chances they actually have cancer? Ooh, so we're looking for our false negatives. So let's subgroup. So we want the people with negative mammograms. And of that subgroup, so we have 4,216 people in that subgroup. And of those 4,216, 8% came back, they actually have cancer. And so it's a really, really small amount. It's, you know, 0.2%. Um, so that's good. I'd rather the test be wrong on, um, the positive test, or sorry, I'd rather it be wrong on, your false positive end than your false negative end. Hopefully this sort of helped you think through these testing tables and how we can use them to find probabilities.